Okay, our next topic is statement with multiple quantifiers. Let's start with a motivating example. And by the way, what we cover here corresponds to section 3.3 in the textbook. Suppose you're visiting a factory that manufactures computer microchips. The factory guide says the following. So there is a person who supervises every detail of the production. So what he said is there's a person who supervises every detail of the production process. So what is the exact meaning of this sentence? There can be two different meanings, which seems both okay from reading the sentence. The first one is there is a single person who supervises all the details of the production process. And the second one is there is for every production detail, there is a person who supervises that detail. Okay, let me repeat this. In the first interpretation, there is a, let's call this Superman, because it supervises so many production details. There is a person who supervises every detail, and you have detail 1, detail 2, detail 3, detail K. Okay, such that this person supervises the first one, supervises second one, supervises third one, supervises last one. It supervises everyone, every detail. And the second interpretation is the following. So for detail 1, I have a person to supervise. And for detail 2, I have a person to supervise, maybe the same person. And for detail 3, maybe I have another person 2, to supervise this detail, and so on and so forth. For detail K, maybe I have a person L supervise this detail. That means for every detail, I can find a person who supervises this detail. Such ambiguity is not allowed in mathematics. Okay, the first one we can say is there exists X. Sorry, there exists a person X. And such that for all detail Y, we define the predicate X supervises Y. Okay, this is the first interpretation. And the second interpretation is for every detail y, for every detail y, there exists an x such that predicate x supervise y. Okay, so you can see in both cases, we need to use multiple quantifier to describe this statement. Okay, the key point is everything within the scope of a quantifier, you can be thought of as a propositional function. So what I mean is, in order to interpret a statement with multiple quantifiers, you can keep in mind the following things. First is, so everything within the scope of quantifier can be thought of as a propositional function. For example, if we have the following statement, for all x, there exists a y such that x plus y equals 0. And we can think about in this way. So for all x, px, where px is the statement, the propositional function, where px is defined to be there exists a y such that x plus y equals 0. So that means we interpret this as a px. So in this way, we can simplify statement with multiple quantifier as a single quantified statement. And then we can look into the detail of the predicate and expand it to study with the property of that propositional function. The second one is, a key point is thinking of quantified statement, quantification as loop. We are going to see this shortly. Okay, let's move to the next page. The order of quantifier. The first one, the first example we are going to see is if the quantifier look like this for all x, for all y, pxy. Okay, the key point here is we can realize that we can merge these two quantifiers, two universal quantifiers together. We can say for all pairs of xy, pxy. So the conclusion here is if we have a consecutive sequence of universal quantifiers for all x, for all y, for all z, and so on, for all w. and we have then we can say this is equivalent to say for all pairs x, y, z, w. That means we can merge multiple universal quantifier and adjacent universal quantifier into a single universal quantifier. So here is very important that we cannot have some exponential quantifier in the middle. We must have a sequence of universal quantifier. Okay, let's give an example. How do you verify the truth of such a statement? You can think about this is, so suppose for simplicity, we assume that x and y just take integer values. So what you can do is to write a very simple program, right? You can say set originally set flag to be 0 to be 1. Okay, and then you say for x equals 1 to n, and for y equals 1 to n, you have a double loop, and if pxy equals 0, so you want to break up the loop, right? So whenever, because for this universal quantifier, the statement is false whenever you find a counterexample. You find a single counterexample. So whenever you find one thing counterexample, you can stop and say, okay, this predicate is false. So what you can do is you set a flag to 0, and when I was trying to search for a solution for programming solution for this, I learned that this is one of the very few places you want to use go-to statement in programming language, because when we learn programming, we are warned to never use go-to statement, but it's turned out that here is a good place to use go-to. Okay. Suppose this is and blah blah blah. You just go to here. You just break all the way from the double loop. Okay, and let's look at a second example, second case. Suppose we want to say the quantifiers look like this. There exists an x, there exists a y, pxy. So we have two consecutive exponential quantifiers. You can see easily that the same thing here is we can combine these two quantifiers, exponential quantifier, into a single exponential quantifier. That is, there exists a pair of xy such that pxy. And the same thing here, we just to check this, you can think about this also. We're doing a loop, but instead we originally set flag to be 0, and whenever we find a predicate, a pair xy satisfying this predicate, we can stop and we return true. Okay, I'm not going to repeat that. Okay, the third case is for all x, third, there exists a y such that pxy. Oh, sorry. I'm sorry. Sorry. From these two examples, okay. So what conclusion we can learn? We can reach. So the conclusion we can reach is we only need to consider alternating quantifiers. Okay, so there are two possibilities. One is for all x1, okay, there are two possibilities. The first one is we start from essential quantifier. Exists for all x, there exists x1 such that for all x2, there exists x3 such that for all x4, and so on and so forth. Or for all x1, if we start we start from universal quantifier, then we are going to have a statement like this. So there are only these two possibilities we need to consider. And very interesting situation is this statement. You may wonder what does it mean. Does it have application in real life? I can give you a very simple example. If, for example, in the first one, there exists x1 such that for all x2, there exists x3. This you can think about this. We have when you play chess, that means the first player has a winning strategy. Strategy. So what does it mean? That means the first player, you can think about the first player, x1. So first player has move such that no matter which move the second player choose, the first player has a second has an x3 move, and so on, such that the first player win. And the second one is it's somehow like the second player has a winning strategy. That means no matter for all move the first player choose, the second player has a winning move. After that, and no matter what you move, the first player move no matter what move the first player choose, the second player has another corresponding move, such that at the end the second player win. Okay, this is showing a very simple example for this alternating quantifiers. Okay, so the third case we need to consider is for all x, there exists a y, pxy. This one is, let me give an example of this one, this situation. For example, for all FIU student, there exists a room Y, dorm room Y, such that X lives in room Y. So what we can think about is, this is saying that every student has a room number, or you have correspondingly, you have room number. So we can, therefore, we can think about this Y as a function of X. So you give me a student number, you give me student X, I can tell you which room that student live in. And maybe there are several students live in the same room. Okay, so that means maybe Y x1 equals Y x2. Okay, let's move to the next page. The next example, next case is there exists an X such that for all Y, Pxy. So this corresponds to the case that, for example, there's a course X such that for all student Y in the, for all student Y in the college of science and engineering, X must take Y. Okay, for example, maybe this course is calculus 1. Okay, so you can think about the pictorially is look like this. X is a universal certificate, X. And so that Y1 need to take this course, Y2 need to take this course, YN need to take this course. And in the previous example, we have student X1 student X1 maybe it live in room Y1. Student X2 maybe live in room Y1. Student X3 maybe she live in Y3. And maybe student X4 live in Y4 and so on. So every student has a room, but their room may not be the same. Okay. So the next topic we are going to discuss is translating mathematical statement. Into statement with multiple quantifier. Sorry, by the way, this statement with multiple quantifier and sometimes are also called nested quantifier. My pen is not working. So statement with multiple you can say it's a statement with multiple quantifier or with nested quantifiers. I'm going to show this by giving you examples. The first example is when we say the sum of two positive integers is always positive. So we want to say, we want to translate this into a propositional statement involving nested quantifiers. So what we can say is, we can say is for all x in Z++, for all x in Z++, for all y in Z++. Okay, x plus y in Z++. According to our previous discussion, and you can also say that for all xy in Z plus x plus y in Z++. That is, you're right. You can merge these two universal quantifier into a single universal quantifier. Okay, the second example is how do we translate this every real number except 0 has an inverse, has a multiplicative inverse. Multiplicative inverse. And such inverse is sometimes called reciprocal. That means for all x, there exists a y such that x times y is equals 1. Okay, so how do we translate this? We so just what's this? We just said for all x in R. Okay, so I think probably we haven't covered this, but so we use this backslash notation to denote side minus. Okay, that means from set R, I just get rid of the set with a single element 0. Okay, that this corresponds to the statement every real number except 0. Okay, we are going to see this later, I think, in module 5. For all x in this, for all real number not equal to 0, we know that there exists a y in R such that x times y equals 1. And also we can write this as implication. For all x in R, if you don't want to use this notation, set subtraction notation, for all x, if x not equal to 0, it implies there exists a y such that x plus y, x times y equals 1. Equivalent form. Okay, let's move to next page. The third example is more complicated. It's the limit. So I believe every student in this class has already taken calculus. So you know what the meaning of a limit fx equals to L means. It means for every real number epsilon, let me write, for every real number, maybe it's a good place to refresh your memory of the calculus. For every real number, epsilon bigger than 0, no matter how small epsilon is, right? There exists a real number delta bigger than 0. So delta is actually, you can think about delta as a certificate of this epsilon. So in general, delta is a function of epsilon. And such that whenever whenever 0 less than the distance between x and a is less than delta, then the distance between fx and L is less than epsilon. Okay, so how do we translate this into a mathematical statement, a logical statement using multiple quantifiers? So first, we need to use universal quantifier, right? For all epsilon bigger than 0, there exists delta. And here, whenever this is another universal quantifier for all x, if you've satisfied the condition x minus a, the absolute value of x minus a is between 0 and delta, then it implies fx minus L, the absolute value of fx minus L is at most is less than epsilon. Okay, so so this is the most complicated example we have seen so far, involving multiple quantifiers. So first, our statement state that for every you pick any epsilon. Okay, so no matter how small epsilon is, I can find another real number delta, such that as long as remember the picture here is as long as your x land in this region, and then the distance between fx and L is at most delta. So the distance here is, this is delta and this is delta, upper bound and lower bound. Okay. Okay, I'm going to stop here for this video. Thank you.